Right, hello. Today we're going to look at multivariable calculus, okay, and in particular directional derivatives. Right, but before we dive into all that, have a quick look at what multivariable functions are first. You know already from your standard maths in even at GCSE that a function has one input, alright? Then we do something to that input and we get an output. So you can think of that like a machine. I put some inputs in, any value of x I want. If I put a value of 2 in and the function's x squared, my function of x will be 4. Alright, so I put 2 in, I do something to it and I get 4 out. I put 9 in, I do something to it, I get 81 out. Alright, so you throw an input in and it kicks something out after doing something to it. Now, I can graph that, on a two-dimensional Cartesian plane with x on the horizontal axis and the function of x on the vertical axis. Yeah, and in this case, x squared gives me a nice parabola. So we're pretty familiar with them. I like to think of it when I introduce this in the lower classes. Look, I've got a pig. I stick it through a factory and I get sausages out, alright? I shove something in, I do something to it, and I get something out. Alright, that's one way I like to look at it. Now, so that's a single variable function. This one down here, now that function there, it's a multivariable function. In this case, it's got two variables for inputs. Alright, the thing I do to it is this. I have each input, I manipulate it a bit, and I'm going to get an output. So let's look at our function machine. I stick an x in, I stick a y in. There's me two inputs there. Now. I only had one input here. I stuck a 2 in, I got a 4 out. This time I've got to stick two inputs in. And if I stick them two in, a 2 and a 3, into this function x squared y, 2 squared is 4, y is 3, 3 times 4 is 12. So I put them two numbers in, I get 12 out. I might want to call that z, alright? Two inputs in, I get one input out, I can call it z. And for this particular arrangement, I can represent that on a three-dimensional graph with three axes, the x-axis, y and the z-axis. So for them particular inputs here, I put 2 and 3 in. That would equate to these points here. 2 on the x, 3 on the y. That would get me to that point on the xy plane. And for them particular values, it creates an output of 12. And I can represent 12 on the, the vertical axis there. So that would be a point in three-dimensional space. Alright, and I like to think of that as, again, going back to my factory analogy, I stick a pig in and a cow in this time, not just a pig. I stick a pig and a cow in, alive. They get mangled up in the factory, and at the other end I get a double bacon cheeseburger. Alright, so that's sort of an analogous to a multivariable function. Okay, now we can move on to an example of a directional derivative. Right, so the next bit, I'm going to do an example here of a directional derivative, okay? It's multivariable calculus, directional derivatives. The example question I'm going to use, it's quite a simple function, okay? I need to find the slope of this multivariable function here with two inputs. The function is x squared y at this certain point in three-dimensional space, okay? X, y and z coordinates in the direction of this vector 1, 1. Alright, so that's what we need to do. We need to find the gradient of that function at this point in that direction on the xy plane. Alright, what I want to do now is have a look at a little three-dimensional graph of this function and see if we can get more of an idea of what this question even means. Alright, it's differentiation, but now we're talking about 3 dimensions, so it's a bit more complicated. Alright, so let me find a 3D graph of this. Right, so here's a 3D graphical representation of the function x squared y. The point I'm interested in here, I've set these scales up, so that point there, that's the position in 3D space. X is -1, y is -1, and z is -1. Alright, and what we want to do is find the gradient at that point as we move away in this direction, right, because that's the y-axis, this is the x-axis, the direction vector was 1 and 1, right? So that would move away at a diagonal position. So as we move away from this point diagonally, what's this gradient doing? You can see it's rising up there quite steeply. So I don't know what answer we're going to get for this, but I would expect the answer to be a positive gradient, right? It should at least be positive, right? And it looks to be, if it was a gradient of 1, it would kind of go that steep, but it looks like it's a bit steeper than 1. So I'm expecting a positive gradient a bit greater than 1. All right, that's what I'm sort of expecting. And graphically, that's what we're doing. We're trying to calculate the gradient at that point, moving off at a 45-degree angle. Right, so the direction derivative, right? Let's look what it means in words. The direction derivative equals the unit direction vector, that's this thing, multiplied by the gradient of f. Alright, so let's look what this means in like mathematical symbols. The direction derivative, okay, it's the upside down triangle. It's a little v with a vector symbol on top. So that's the direction vector. I'm calling mine v. And f is the function. So that reads this part here, the direction derivative of f in the direction of v, and that's what that bit means. Right, so there's my direction vector there, AB. The direction vector, and to make sure it's a unit direction vector, I have to divide it by the magnitude of the vector. Okay, this should be familiar if you've done vector studies in year 13. So these two lines here mean the modulus of this vector multiplied with the gradient of f. And the gradient of f is built up, it's a vector formed with the partial derivatives of the inputs here. Right, so another way I can write that is my direction vector multiplied by the gradient of f. Right, that's a really shorthand way of writing it. Right, and that equals this, which is the direction derivative. Right, for this part, I'm not introducing partial derivatives today, so you'll have to look at that somewhere else, alright? But the first thing I need to do is check whether my direction vector is a unit vector. So a unit vector of 1, 1, that means I've got 1 across in the x, 1 up in the y, and I can see the length of that vector would be root 2. Root 2 is bigger than 1, so it's not 1. I need to make this vector, I need to shrink it a bit so that the length of it becomes 1. So how do I do that? Well, I take the values of it and divide it by whatever the length of the vector was. So it's 1 over root 2 and 1 over root 2. The problem with this is I don't like having roots in the denominator, so I'm going to rationalise the denominator and we end up with this. So this vector here is our unit vector. And the next part is I need to do my partial derivatives, df over dx and df of dy. Alright, for partial derivatives you've got to use these little curly d's, and the first one I'm going to differentiate my function with respect to x. That means I need to treat y as a constant, but when I differentiate the x, that's going to be 2x, and it's going to be 2x times me constant. So I end up with this 2xy. Alright, for the next one I'm going to differentiate my function with respect to y. This means x squared is constant, and we think of it, x squared is held constant, and we think of it just as a constant. So if I differentiate y with respect to y, I get 1, and my constant stays there, so it's going to be x squared. Alright, that's going to differentiate to x squared. Okay, and my partial derivatives vector becomes 2xy over x squared. Yeah, that bit there and that bit there. There's my gradient of the function. Okay, now that I've got my gradient of the function, I need to work out what the values of the gradient of the function are at that point. Alright, so I just stick the values in at this point in space where it's asking me to work out, and I've got 2xy, so I need x is minus 1, y is minus 1. So x goes in there, y goes in there, and the x squared, so that's x is there, minus 1, that's minus 1 squared. I work all that out, I end up with 2 and 1, alright? That's my gradient of f, 2 and 1. The gradient of the function at that point. Yeah, it's a vector. Now the last bit I need to do is work out my direction derivative. And I can see, that's my direction derivative here. I need to multiply my unit vector by the gradient of f. Alright, so my unit vector ended up being that. My gradient of f was this at that particular point. So the gradient in this direction, it's a cross product, 3 root 2 over 2. There you go. And that final number is, that final number there, 3 root 2 over 2, that is the gradient of this function at that point in that direction. Alright, absolutely amazing. Right, so coming back to the end, we got a value for this gradient of 3 root 2 divided by 2. Right, and if you bang that in a calculator, it gives you a value of about 2.1, right, positive 2.1. And that's great because as I move away that way, I'm going up here, it looks like it's steeper than 1. In fact, it looks about 2. We got a value of 2.1. We got a positive value, and it's a positive increase. So our value actually looks great when I look at this 3D representation of the function. Okay, so that's quite a good exercise to do. Alright, quite nice to see it represented graphically, and it gives us a feeling that our answer is correct as well. So it's all good, it's all good.